Patterson here. Today we're going to go over Enzymes, AP Biology, Unit 3. The rate of metabolic reactions, this is part of the law of thermodynamics, and this is going to let us know if a reaction is spontaneous, but it doesn't really describe the reaction. So let's say I have sucrose. So here I have sucrose. If I wanted sucrose to break down naturally without any enzymes, without any help, it is not a spontaneous reaction that happens fast at all. One sucrose molecule without any help from an enzyme could take over 1,000 years to happen on its own. That is just one sucrose molecule. So for me to be able to go from sucrose to two different types of macromolecules, my glucose and my fructose, I need help. And I need that help in the form of an enzyme. Enzymes, these are going to be proteins, and they can speed up reactions by lowering what's called the activation energy. If you remember in our last video, the free energy, we talked about exergonic reactions, and this is when energy is released and the reaction is spontaneous. It's going to happen on its own. This purple line right here, this is the line of the spontaneous reaction. I'm going to have a little bit of energy that has to go into it, and then I'm going to have a lot of energy that can come out, and this energy is going to be used to make my products, break down my molecule, break down with the enzyme, or break down the molecule. But I can have an enzyme help, and this green line here, this would be an enzyme. Look at how much lower this hump is compared to this purple one. This is a lot lower of a hill to have to climb. So there's a lot less energy that the cell or the molecule is going to have to put in to be able to make this make this reaction happen. So this enzyme is lowering the activation energy of this reaction. It is helping to make the catalyzing of this reaction a lot faster. So enzymes are made of proteins, and we know that proteins are made up of amino acids, and they sit in a specific sequence, and they string up to make peptides. These peptides have to be in a very specific order for very specific enzymes. They are going to fold a very specific way. If the fold of this protein does not fold correctly, the specific enzyme function is not going to be the same. So this is one thing about enzymes that students need to really understand, is if I change the shape of this protein, I'm changing the function, and that goes with enzymes. I change the shape of the enzyme, I'm changing the function of the enzyme. So enzyme structures, I have the enzyme. It's going to be very specific to very specific substrates. This substrate is square. This is going to fit in this spot here. If I had another enzyme that had a square-like shape, this would not fit that spot. If I had a circle substrate, it would not fit this. It would just come in and bounce back out. Only this substrate will fit in this little area right here. We also call this the lock and key model. If I put a lock in my door, it's going to unlock it. But if I put a key in a lock up and down the hallway at our school, I'm not opening up any doors. It's very specific. Enzymes are very specific to specific substrates. We call this area our active site, and this is the area where the substrate will bind. We also have what's called induced fit. The enzyme will adjust the active site to make sure that the substrate fits more snugly. So what happens is you're going to have an enzyme, and I have my substrate, and this is my active site. This substrate is going to come into this active site. This substrate is for this enzyme. And then as it comes in, you can see it doesn't really fit real snug. The enzyme can shift and move and come in and hug it, and it's going to make it a lot tighter, so it's easier to break those bonds. And how an enzyme works is it's going to go in like that substrate. It's going to take it and it's going to hold it and it's going to stretch it, And as it pulls it, it's going to open up these areas for these bonds to be more open to the water, for water to come in and help hydrolyze and break these bonds, or for dehydration synthesis to happen where I can put these pieces together. So enzymes are good at pulling these molecules in very specific ways to allow the hydrolysis and these breaking of bonds to happen at a lot faster rate. We have different types of reactions. We have catabolic. These are going to break substances apart. So I have a substrate, and substrates are just molecules. This could be sugar, this could be some type of lipid, it's going to be some type of molecule. So a substrate is not just some magical substance, it's going to be a molecule of something, but it's a substrate if it's going into an enzyme. So the substrate goes in, and here I have an active site. This is very specific for this shape. Then I'm going to have the enzymes going to come together. We make an enzyme substrate complex. This enzyme is going to grab the substrate, is going to pull it and put tension and force on it, stretch those bonds, and then water is going to come in and lyse it. I'm going to hydrolyze those bonds. Now I'm going to have two different pieces, and these are now called products. When they leave the enzyme and they've been changed, these are now products. I have people remember catabolic. You have cats. If you leave anything on a counter, cats don't like it there. They're going to knock it off and they're going to break it. Cats can be jerks. So you have a catabolic reaction. They are going to break stuff. Anabolic is going to put stuff back together. So here you can see I have two different substrates. They're still substrates, and they're going to come in and they're going to fit into this active site. The enzyme is going to twist these pieces together to where I can have dehydration synthesis. Water is going to come out of those bonds and cause it to come together. Then the enzyme is going to relax, and now I have my new product can be released, and it's going to leave the enzyme. When I look at certain graphs, I have to look at the enzyme reaction and my substrate concentration. So here, as I go up, my rate of enzyme reaction increases. Here, the amount of substrate concentration increases. So I get more, and I get a higher rate of reaction going this way. So when you look, I have a low concentration of substrate, so I have a low reaction, but it's reacting at an increased rate. Then I come up here and you notice I stop and I start going flat. So this line here is saying that the reaction rate is followed this pattern when the enzyme amount is fixed. So let's say I only have 100 enzymes in this solution that are working. There's going to come a point, and this point's right here, where I'm going to have a site saturation. I have my 100 enzymes and I have the substrate concentration. When I get to this point right here, this is the amount of substrate that I can't make the enzymes react any faster. If I add more substrate, it's not going to make my enzymes react any quicker. These 100 enzymes can only react with so much substrate at one time. And this is the point where I will not be able to increase my reaction rate. I'm still working, I'm still breaking down substrates, but I will never be faster than this point. So this area right here is going to be where I'm saturated. So the active sites are saturated. No further substrate is going to increase my reaction rate. I can only increase my enzyme reactions if I increase the number of enzymes. So now if I had 100 enzymes and I added 100 more, now I would see an increase because now I'll have more enzymes available to be able to metabolize the substrates that are in the solution. Enzymes are made of proteins, remember, and enzymes can break down to certain things. One can be temperature, it can be pH, it can be chemicals. So remember, these proteins are folded very specifically. Remember those R groups, those side chain interactions is going to cause this to come together. If I have an increase in temperature an increase or decrease in pH, chemicals come in, we call it denature. And that's when these bonds start to fall apart, they break. And if I denature something, I cannot renature. So when denaturing happens, my bonds are all falling apart and they're just becoming, they're not folded correctly. And remember the number one rule with proteins, if it's not folded correctly, it's not going to function correctly. So this has to have a very specific fold for a specific function. So let's look at this graph. I have a temperature enzyme graph. Again, my rate of enzyme reaction increases and my temperature increases as I go this way. I see that I have the enzyme reaction increases as my temperature increases, and this is going to increase due to the temperature and the molecular change. Remember, when things get warm, when they get hot, the molecules start to move faster. So the hotter it gets, the faster it gets, and they're just going to start bouncing all over the place. When they start to increase in temperature, you get to a point where they're able to they're going to bump into each other more, and there's more opportunity for bonds to be exposed to be able to break down. So temperature and enzyme activity can increase due to motion, but there comes a point where you can get too hot. So here, this is the perfect temperature for this specific enzyme. If I go past this point a little bit more, I'm going to start to fall apart. And what happens is this part here is going to start to denature. My bonds are going to start to break. Here I can increase. My temperature is going to cause these enzymes to start moving faster, 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 faster. And then there's going to be perfect. And then it's going to be too fast and they're going to start falling apart. And then all of a sudden I've got issues. So this is increasing enzyme activity. This is my optimum temperature to a certain point. Okay. And then after that, I'm going to start to denature. My protein is going to start falling apart due to the heat. I can see the same thing with pH. Here I have pepsin, and here I have very acidic, and I go this way, very basic. So remember, acids are a lot of hydrogen protons floating around in a solution. Bases have a lot of hydroxyls floating around in a solution. So pepsin loves to be in a pH of 2, which is good because that's in your stomach, and your stomach has a very high acidity. So this pepsin enzyme works very good for that. If this pepsin enzyme happened to get into your blood, so let's say your blood is about 6.8, all right, is this enzyme going to be able to function in a 6.8 pH? No, it's going to fall apart. And that's good. I don't want pepsin to be able to work like that in my bloodstream, and vice versa. I don't want certain enzymes coming in and affecting my stomach acids either. So this enzyme works perfect with the 2. The amylase, which breaks down sugars in your mouth, this is going to be about 6.8. And arginase is going to be good at about 9.5. Now, can pepsin work at a 3? Yes. Is it going to be very good at what it's doing? No, but it still can. Once I get down past 4, I'm not going to have any enzyme production, especially when I get to 5. So you just have to look at these. When I have pH, again, specific enzymes. This enzyme is folded a specific way where it can handle pH of 2. This is folded a specific way where it can handle 6.8. This is folded a specific way to have 9.5. So being outside of this normal pH can cause these hydrogen bonds to break, because remember, acids have a lot of those hydrogen protons, and this will change the shape of the enzyme. You also have what are called cofactors. Some enzymes require a cofactor to be active, and these are going to be non-proteins. So here I have a substrate, and I have this little Pac-Man guy right here. This circle will not fit in here, but I can bring in a cofactor that will have a specific shape where it will attach to this active site, but another part of it will help to break down some of these other substrates. So this will come in, my substrate will come in, and then it will break it down. These are going to be the pink little piece right here. This is a non-protein, which means it's inorganic. A lot of them are certain types of metals that you could have, maybe some type of magnesium or something like that. And they call these holoenzymes. And now when this cofactor comes in, this is going to activate this enzyme to allow it to break down the substrate. I have coenzymes. These are going to be organic factors. Organic are ones that are going to have carbon in it. And so organic factors, these are like your vitamins. So like B12, vitamin C. This is going to come in and this is going to hit this active site. And then my substrate can come in and now it's going to be activated to break down that substrate. You can have some, I don't want enzymes working all the time. And there are times when I can have an enzyme be shut off or slowed down. So here I have a substrate, and this substrate will fit in this active site, right? But I can have what's called an inhibitor. An inhibitor can be created by other enzymes when I have too much of one substrate going on. I can create inhibitors, and these inhibitors will come in and they will fuse to this active site. So now if this substrate tries to come in, it can't. It's just going to get bounced back out. So we call these competitive. These are competing for these active sites. This is preventing the substrate from coming in. And so when this happens, I'm slowing down this reaction of breaking down the substrate into smaller pieces. So this is a competitive inhibitor. It's going to inhibit this, but it's competing with these active sites. That's the best way to remember that. So competitive inhibitors, they're going to reduce this enzyme activity by blocking this active site and preventing this substrate from coming in and binding. Inhibitors, that's hard to say. The inhibitors can be reversed with an increase in substrate concentrations. So see these inhibitors, I've got these inhibitors in here, but the more substrates I have coming in, the more opportunity I have for these enzymes to break down these substrates. If I have very few substrates, these inhibitors are going to be able to prevent these substrates from breaking down. But the more substrates I have, the more opportunity I'm going to have to hit these active sites. You also have what are called non-competitive inhibitors. And so this substrate's going to bind here, right? But I can have one that can bind to a second spot. So this spot will bind right here. So I have what's called an allosteric site, and this is an allosteric site. This is the site that this substrate is not going to want to bind to. The substrate wants to bind to this active site. But this allosteric site can bring in a different type of substrate. This is what's called a non-competitive. I'm not competing for this active site. I can come in and I can land in this site. And what this does is it causes a conformational change in this enzyme. It's going to change the shape of the enzyme. And remember, you change the shape, you change the function. So this will come in and it will sit in that site. And then when it does, it's going to cause a change. And now all of a sudden I have a change in my enzyme. This substrate can no longer fit in this active site. So this is also a way where I can shut down enzymes to prevent them from breaking down more substrates. So that won't go in and it's going to bounce off and go away. I can regulate chemical reactions. So cells have to be able to turn on and turn off their ability to break down substrates. So we have to be able to turn them on and off. So these non-competitive inhibitors can be part of that process. I can have an enzyme that will make these, and then as it makes a lot of these, it's going to start shutting down these enzymes. And then once I have more substrate come in, these can start breaking down, and then I can start making more products with these substrates. So allosteric regulation, you have two binding sites. I have my active that the substrate wants to bind to, and then I have my allosteric, which is another piece of material, some type of inhibitor that will come in and fit this site, cause this to change. I can also have ones that can have multiple sites. So here I have these active sites here, and these little pieces here can be an allosteric site. So let's say this is an inhibitor. This inhibitor can come in here and close down these active sites. I can close down multiple ones at one time. So this one's going to come in. This is going to be conformational change. I'm going to cause that, and I'm not going to be able to allow my substrate to come in. Here I bring in my inhibitor. It's going to go in, and then when it comes in, it causes a conformational change that hits all of these, and then all of a sudden I've changed my active site where the pieces can't come in. These activators can be activated, and so when they're activated, I can have a piece come in. So this is an activator. Here I have an active site for the activator, which would be this part right here. This is an active enzyme, active substance. So when this comes in, it's going to cause a conformational change that can activate all of these pieces. So it's going to come in, it's going to bond, conformational change, and then all of a sudden all of these pieces are going to become active. I can also do the other. If I want to make it non-functional, I don't want it to be active anymore, I can bring in a different inhibitor. So now I'm inhibiting it. It's going to go in, and then it's going to activate, cause this to do a conformational change, and it's going to inactivate that. So now I have an inactive form. So I can turn on multiple at once, turn off multiple at once with an inhibitor or an activator. I can have ones that are cooperative, and these are going to be where I have a substrate that can come in and bond, and then it causes everything else to open too. I can cause these other pieces to stay open. So this substrate will come in, it will go fit in the little slot, and then it causes a conformational change for the other pieces and causes it to open. This leaves, and then everything will close back up. You also have feedback. So this is kind of really interesting where enzymes can make pieces. So here I have substrates, these little green triangles. These little green triangles can come into an enzyme, and then when it comes into an enzyme, it can make a product. And this product can be used on a different enzyme. And so this purple triangle got made by this. This purple rectangle got made by enzyme 1. This purple rectangle attaches to enzyme 2. Enzyme 2 then makes this little jagged little blue piece. This jagged little blue piece comes along to enzyme 3, and it makes a yellow triangle. Okay, so this purple or this green triangle can go to make the purple, to make the blue, to make this yellow square. This yellow square can be an inhibitor. This can stop the production or the breakdown of these other pieces. It's not going to allow these green triangles to bond. So this can inhibit and stop the production of A and B and making of these little squares. So the less squares I'm making, the more these enzymes are going to kind of do their job. These squares are going to be left, they're going to be broken down by something else, maybe another enzyme will use them, and then when this leaves, it's going to open it back up again to where these triangles can start making rectangles, making blue squigglies, and then I'm going to start building up my yellow square concentration, and then I will start to make more inhibitors to stop it down. This is kind of what happens with insulin. When you eat a lot of sugar, your body starts breaking down sugars, but then it starts making markers to make insulin. And so insulin's going to come down and start breaking down sugars. I don't want insulin breaking down every bit of sugar in my body. So there are products that are going to be created that are going to start to attach to enzymes that start to make the insulin or send out the insulin that's going to start to slow that process down. So I'm not breaking down all of that sugar. And then once the sugar levels leave and then I eat more sugar, it's all just going to keep going back into this cycle. All right, so the product's going to bind to my allosteric site, okay, and it's going to continue until the product is used up by the cell. So the cell will use up the product, and then it can start the cycle again, and then once this fills up, it will stop, and it will just keep going into this loop. Okay, that's going to be enzymes, AP Biology. If you guys have any questions, you let me know. We'll talk to you later.